In this example, we're going to look at weight gain during pregnancy. So the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9. Weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines that their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? To approach this problem, let's first identify what the mean weight is in the very first sentence. So when I look at this mean weight, I need to make sure that I understand that that mean weight of 30 pounds is information about the population. So we're going to identify that as mu equal to 30 pounds, and therefore the standard deviation is a population parameter, so that's 12.9. Weight gain during pregnancy is skewed right. So the shape of our population distribution is skewed right. The third sentence, an obstetrician obtains a sample of 35 low-income patients. So we have a sample now of 35 patients, and the mean weight gain during pregnancy for these 35 patients, so X bar, the sample mean of these 35 patients, was 36.2 pounds. Does this result suggest anything unusual? The question that we're asking here is, what is the probability of getting an average weight gain greater than or equal to 36.2 pounds from a sample of 35 women? In other words, was the result that the doctor had from a sample of 35 women, was that result unusual? So if we wanted to talk about the probability of an event, that's where we're going to use our normal calculator to calculate the probability of that event, the area under the curve. So we want to first identify the shape of our distribution. So the shape of our sample distribution is coming from a skewed distribution. So the population is skewed, but the central limit theorem says that as long as my sample, which is equal to 35, as long as the sample is greater than or equal to 30, then the central limit theorem guarantees that the sample mean distribution ends up being normal. And so we have met that minimum threshold, and so the shape of our sample distributions will move to be a normal distribution, even though the population's shape is skewed. The center of our sample distribution says that the mean of our sample mean X bar is equal to the mean of the population, or 30. And then the spread of the sample mean, which is sigma X bar, can be calculated by taking the standard deviation of the population divided by the square root of n, or in other words, 12.9 divided by the square root of 35. And when I do that using my calculator, I find that the standard deviation is 2.1805. So that's the information I'm going to use to now put into my normal calculator. So that information goes into my normal calculator from StatCrunch, which you see on the right-hand side of our screen over here. So with a mean of 30, a standard deviation of 2.1805, we are looking at the probability of an average weight gain greater than 36.2. And the likelihood of that happening is 0.0022. So 0.002. So in 1,000 different samples of size 35, we would only get 2 samples out of 1,000 that would have an average weight gain more than 36.2. So this is an unusual event to have happen. So here you can see that I've added to the screen an interpretation of our probability that we just calculated using the normal calculator. So we said that the likelihood of a sample having an average weight greater than 36.2 pounds is 0.002. And you can see here that that means that in 2 out of 1,000 samples, that's only going to be 2 out of 1,000 samples that result in an average weight gain greater than the 36.2 pounds or higher if the population average weight gain is 30 pounds. And it's kind of interesting to see the two conclusions that can happen here. You could have either had a group of 35 patients who just were randomly selected and they happened to have gained more weight. So maybe I got a group of women who just gained more weight randomly, like I randomly selected the 35 people who happened to gain more weight. Or the second conclusion could be that the average weight gain for the low-income patients is really more than 30 pounds. So in other words, if that's the case, if the average weight gain for low-income patients is not really 30, it's in fact 30 pounds, that's actually a statement saying that my assumption from the beginning that your average weight gain of 30 pounds that we claim from the population, it's a statement against the population. And it's an interesting thing to think about because it is the premise behind us looking at hypothesis testing later on in the course. And you can read the reasoning why they might look at the second conclusion as opposed to the first.